All right, we have our first medium exercise, and this one definitely lives up to the hype. So we have an infinite plane, we have a robot that stands at the origin, x coordinate is 0, y coordinate is 0, faces north, and yeah, it describes the directions in terms of the axes. The robot could either go straight 1 unit or turn in either direction. And we want to return true if and only if there exists a circle in the plane such that the robot never leaves the circle. So let's look at these examples here. So here we have you go forward 2 spaces, turn left twice, and then go forward 2 spaces. And so basically you start at the origin, you go up 2 spaces, and then you turn back around, and then you go back to the origin, and then you just keep repeating. And so that is it is true that there is a circle that the robot never leaves. I don't like this word circle, by the way. This really bothers me because it's like, I don't know, what they should say is that like there is a path in the plane such that the robot never leaves the, well, there's a closed path, there's a finite path, or a bounded path within the plane such that the robot never leaves the path. All right, we have another example. You just go forward. Like if you just keep going forward, then you're never going to, you're not going to be in a bounded circle because you're just going to keep going off and off to infinity. So now we have this example here where we have go forward, then turn left. And so basically you go up 1 spot, then after turning left, let's see here. So that's going to be, let's draw this out. So you're going to start at the origin here, and you're going to go forward, and then that'll mean you're here, then turn left, then go forward again, then turn left, then forward again, then turn left, and then you're back at the origin, and so you just keep going around in this circle. Okay, so what are we noticing here? Let's actually do, so with these sorts of problems, the more, like if you don't understand the problem, or if you need to build intuition, the best thing you can do is just do some examples. So let's try some more complex examples. So let's say we want to go straight. I'm just thinking in terms of like, I don't know, let's think of like knight movements in terms of like chess. So let's say you go forward twice, and then you turn right, and then you go forward once. And so just an example. So you start at the origin, then you'll go up, up, turn right, and then go forward 1. So at step, at the beginning, so I'll call this step 0. You start at the origin and you're facing north. Then you go, you turn right, and then you go. And so here after step 1, you're up here and you're facing to the right. Then you go forward, forward, turn right, go down. You're facing this way. This is after step 2. Then go forward, turn right, go forward, facing this way. This is step 3. Then go forward, turn right, go forward. This is step 4, and you're back at the origin. So this is a circle. All right. What's another example that we could have? Let's do, let's say we do the same movement. We end up at the same spot, but let's say we turn around. So we'll start at the origin, step 0. Go forward, turn right, go forward again, and then we're going to turn around, so now we're facing this way. That's what turning left twice will turn us around. So this will be after step 1. Then go forward, turn right, go forward. No, turn right. We'll go up this way. So forward, right, forward, and then you turn around by going left twice. And so you'll be here, pointed downward after 2, and go, right, go, turn around here, then go, right, turn around, and you're back at the origin. Okay, so what are we noticing in these examples? So there are cases where you just like keep on walking off. But if it's not the case that you keep on walking off, then what happens is you could either have something like this where you like, could have something like this scenario where you like, you go to you start at the origin, you go to one place, and then, so basically, it says it here in terms of like the cycle of the individual steps, but we can think of this in terms of like iterations through the instructions. So in this example 1, you start at the origin. After going through the instructions once, you end up at some other point. And then after going through the instructions twice, you end up back at the origin facing north. And then you repeat that again. Okay. So that's a possibility where basically either after going through, obviously if you don't move, then you're in a closed circle. If you go, there can be a scenario where you go through the instructions twice and you end back up at the origin facing north, and then you just start over, so that's a cycle. But then you can also have examples where you end up, you run through the instructions 4 times and then end up back at the origin facing north. Okay, and so what's the difference here? So, or what's causing the difference in scenario between these having cycles and not having cycles? So, in all of these examples where you have cycles, let's see here. So you could either well, first of all, you have to not end up at the origin. And then the only other thing is you have to not be facing north. Because basically, if you think about it, what's going to happen is that if you can have scenarios like this where if you end up facing backwards, then if you end up facing backwards after the first run through the instructions, then when you run through them again, you're just going to undo the action that you just did, because you're going to be doing the same instructions but facing the opposite direction. And so the path you're going to do is going to be just the exact opposite, and so it's going to undo exactly what you just did, and you're going to end up at the origin. So that's what happens when you end up facing backwards. If you end up facing left or right, then what's going to happen is when you run through the instructions 4 times, since you're turning 90 degrees every single time, the effects of these 90-degree turns on the instructions causes them all to cancel out after 4 turns, or after 4 runs through the instructions. And so the only scenario where we go off to infinity would be if it's something like this. And what's special about this? Well, first of all, we have to end up not at the origin, because if we end up at the origin, then it's just going to, we're just going to stay at the origin the whole time. So in order to go off to infinity and not form a closed cycle, a repeating cycle, you need to be facing north, and you need to not be where you started. The facing north is important because as we saw, facing south or facing east or west is going to cause you to form a cycle no matter where you end up. So all that matters is that you're all that matters is that you're facing forward and you end up not where you started after one cycle or after one run through the instructions. And if that is true, then you're going to not form a cycle, and so you'll return false. Otherwise, you will return true. So we could just go ahead and implement the logic for this. What I want to do is I've sort of given an intuitive argument in terms of what actually happens here, given our understanding of the problem and based on the examples that we've worked through. But I do not find this, I like giving mathematical proofs of patterns that I see through examples. So we're going to write out a proof of this claim that we need to we end up in a cycle if and only if after one run through the instructions we end up in a cycle if either we remain at the origin or if we are at a different point than the origin and not facing north. Okay, so let's make this mathematically rigorous. Okay, so we're going to have this function L n be the location of the robot after running through the instructions n times, with L of 0 being where we start, which is the origin. So x coordinate is 0, y coordinate is 0. I'm just writing this in vector notation because I feel like it. Okay. Suppose we have this function wait, do I use this? Yes, I do. Okay, so let d be a function from the natural numbers into n, the set of 4 characters, n, s, e, w, and you can sort of guess this is the direction. Describe the direction after n runs through the instructions. With d of 0 is going to be n because we assume that we start facing north. Okay. Let m be a function from the natural numbers into the plane. So I'll just write z squared. Be defined by m of n is going to be ln minus ln minus 1. So that m describes the movement between runs n minus 1 and n. So if you are at a particular point in space after running through the instructions n-1 times, then to get to the next location, you just add m of n. And thus, by definition, L of n is going to be L of 0 plus the sum from I equals 1 to n m I. Because in order to get to the location after running through the instructions n times, you start at the origin. So I didn't really need, well, this is the origin, so it doesn't add anything, so it's actually not even needed. But I'm actually going to include it just so that it coincides with our intuition. To get the location after n iterations, you just take the starting location and then add every incremental movement. Okay, so this is these are all the definitions that we are going to use. Okay, so now let's write our theorem. And I'll just write this as claim. So I claim that the robot does not form a cycle if and only if D1, so in order for the robot to not form a cycle, what needs to happen? The direction after one run through the instructions needs to be north, and the location after one run through cannot be the origin. Okay, and this is a little weird saying, like, claim the robot does not form a cycle if and only if this happens. It might be easier to write the robot does form a cycle if and only if one of these other conditions happens. But the other conditions are that either it's just the negation of this. So it's either D1 is not north, or D1 is north and L1 is the origin. Okay. But anyways, let's go ahead and prove this. Okay. So proof. So we're going to go through like various. We're going to go through cases here. So, if we're going to go through all the possible scenarios for what D1 and L1 could be, and in each one determine whether we end up with a cycle. So if D1 is north and L1 is the origin, we have a cycle. And that's straightforward because you just don't, because if you're going to be at the origin facing north after one iteration, you're going to be there after every single iteration. And so you're never going to leave the cycle that you go through in that first set of instructions. And so this is straightforward. Okay, so that's going to be one case. Here's another case. suppose D1 is S. So our intuition here is, we talked about this already. When the direction after one's run through the instructions is south, then basically what happens is that after the second run through the instructions, you undo everything you did in the first instructions because you're going in the reverse. And so, yeah. Okay, so here's, let's actually do this. So we're going to let M1 be X, Y throughout this proof, because this is going to really help us because all of the other movements can be defined relative to M1. So before we go through the example of south, let's run through this again. So let's suppose that we have G, G, R, G, R. So after one run through, we start here. After one run through, so you're right, go forward, and then right again. So we're here. And then the second one is go, go, right, go. Okay, and so we end up here because we turn right at the end. So after the first, so M1, what did we do? We moved up twice and to the right once. So that's 1 unit in the X direction and 2 units, 1 unit left in the, 1 positive unit in the X direction and 2 positive units in the right direction. On the way back, we went 2 units down in the Y direction and 1 unit down in the X direction. And so we can see that the movement between steps 1 and 2, to get that, you basically just take the negative of the first movement. So let's write that out here. Suppose D1 equals S, then M2, we know M1 is XY, M2 is going to be negative X, negative Y. And D2 is going to be north because after going through the instructions 1, you've turned around 90 degrees. So going through the instructions again will turn you around another 90 degrees and end you up back at north. Okay. So where do we end up? What is the location after going through the instructions twice? Remember our formula. It's the origin, and then M1, and then M2. So I'm not going to write out the origin this time, but writing out M1, we know that this is XY, and M2 is negative X, negative Y. So this is 0. Okay. So we've returned again to being at the origin. So after 2 steps, we're at the origin and we are facing north. So this is a cycle. And I suppose it's it might be worth saying real quick, like, does that guarantee that this is a cycle? And it does, because what you can do is there's like a fixed collection of points that the robot will walk through on the path between iteration 0 and iteration 1. And well, here, let's see here. What we really care about is going from iteration 0 to iteration 2. So the very beginning until going through the instructions twice. In that time, you're going to the robot goes through a finite number of spaces, and it started facing north and it ended facing north at the origin. And so the next time it goes through it will go over the same steps. And so if you want to, for any particular n, if you want, so not using n not to refer to the number of times through the instructions, but the actual number of like movements and the actual number of points that the robot will iterate through. To find where the robot will be at any particular point in time, you just can sort of use, like you could use some sort of like division with remainder to sort of figure out what is, for that n, how many movements are you past the last time that you are at the origin facing north at the beginning of a cycle. And you could use like the length of the cycle, or you could use the length of the instructions to determine this. And so then you would be able to define this point relative to the first time the robot went through the cycle. So that was a very hand-wavy argument, but the point is that the robot returning to the origin and facing north after some number of iterations through the instructions is sufficient for the robot to be in a closed cycle. Or just a cycle. I don't know. These definitions, it's not super rigorous definitions that we're using here. Okay, so that's when we're facing south. Suppose the direction after one iteration is east. Then D2 is going to be south. D3 is going to be west. And then D4 is going to be N. So after 4 runs through the iteration, through the instructions, we're going to end up back north. Okay, so M1. So we know that M1 is x comma y. Okay, so what is M2? M2, let's look at our example. So this one up here was an example where we ended up facing right. So we moved one positive unit to the right and 2 positive units up. So the value of x here is 1 and the value of y is 2. Now going from step 1 to step 2, the movement in the x direction is 2 and the movement in the y direction is -1. And so we flipped the x and the y, and we've added a minus sign in the y direction. Okay, so what that means is that M2 is going to be equal to y comma negative x. Okay. Then M3 is going to be, okay, so here, well, this is just like with the turning backwards face, where we just do the opposite, so minus x minus y. M3 is going to be minus x minus y. Then M4, well, you can kind of see a pattern here, but just to confirm, So it's basically what you do is you reverse the x and the y coordinate, and then you put a minus sign on the second coordinate. But let's confirm that here. Going from 3 to 4, we go 2 to the left, and so minus 2 in the x direction and 1 in the y direction. And so the movement in the x direction is, what we started with was minus y. Or minus y, where y is referring to that first movement. I probably should have used different letters than x and y here, since I'm using x and y to refer to the directions, or to refer to the the axes. But oh well. And then in the y direction, yeah, there we go. So in the second, along the second axis, we move x. Okay. So where do we end up after 4 runs through? So we start at the origin. That's just 0, 0. I won't write that out. So sum from I equals 1 to 4 mi. And so what's your first movement was xy. Then we had y minus x. Then we had minus x minus y. Then we had minus y x. Then this x cancels with this minus x, this y cancels with this minus y cancels with this minus y, this minus x cancels with this x. We get the origin. Okay, so after 4 iterations through the instructions, we have d4 equals n and L4 equals the origin. So this is a cycle. Because there is an n greater than 0 such that dn equals north. Well, and that's another one, because the variable n is very common for you referring to like natural numbers, but the string n is being used to refer to north here. So what we have here is there is a natural number k such that k is greater than 0, L of k is the origin, and d of k is n. And so that's the sufficient condition for this being a cycle. Okay, suppose d1 is Weast. Then d2 is going to be S, d1 is going to be East, nope, d3 is going to be East, d4 is going to be back north. Okay, M2 is going to be, I'll start this, but we'll see the pattern. So it's similar to before. Okay, so here in this example, we went 1 in the x direction and 2 in the y direction. Then the next time we went -2 in the x direction and +1 in the y direction. So the x and the y flip again, but we put a minus sign not in the second coordinate, but in the first coordinate. Okay, so M2 is going to be minus yx. And then this pattern is going to continue. M3, we're going to switch the entries and put a minus sign in the first one. So minus x minus y. M4 is going to be positive y minus x. Okay, then L4 is going to be M1 plus M2 plus M3 plus M4. So it's going to be xy minus yx minus x minus y y minus x. Cancel, 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 cancel. So 0. This is the origin. This is a cycle. Okay. All right. So that's a bunch of scenarios where we have cycles. What's left? The only remaining scenario is, so what is the direction? We know if D1 is south, east, or west, then we have a cycle. The only thing we haven't covered is when D1 is north and L1 is not the origin. So the only remaining scenario is D1 is north and L1 is not the origin. Okay. So D1 is north. So after running through the instructions, we don't change direction at all. So that means that dk is going to be north for any natural number k, because we're never going to change direction. Thus, what is the location after going through the instructions k times? Well, after going through the instructions once, we end up at x, y. And after going through the instructions 2 times, well, there's not any change in direction. And so the movement is, so M2, the movement from step 1 to step 2 is going to be the same as M1, the movement from step 0 to step 1. So L2 is going to be just twice of xy, because you'll just go in the x direction twice and in the y direction twice. So LK, more generally, is going to be k times x, y. Okay. At least let's say x or y is non-zero. Why? So at least one of x and y is non-zero, because if they were both 0, then well, we're not in this case. So we've assumed that one of x or y is non-zero. Remember, x comma y is M1, which is where you end up after moving through the instructions once. Okay. So if we look at the collection of vectors of the form x times y, such that, yeah. So this is basically the path that's traced out after every time you run through the instructions. This path is infinite. Any loop must be finite. Thus, this is not a cycle. Any cycle must be finite. Okay, why must the cycle be finite? Because one way to define this would be to have it be bounded, and within any bounded subset of the integer grid is going to be finite. There's only finitely many points. Yeah. Because if you, yeah, and so if it is a cycle, then at some point you need to return back to where you started. And you must return there after a finite number of steps. And you will go through those finite many steps repeatedly after you return to the origin. And so cycles must be finite. But here we see that the path traced out by this set of instructions is infinite, because either x or y is non-zero. Let's assume without loss of generality that x is non-zero. Then just the x coordinates are going to continually increment by x, and it's never going to cycle back. And so this is an infinite set. So this is not a cycle. Okay, and so now we have exhausted all possibilities. And that confirms the claim, because if D1 is n and L1 is the origin, if D1 is n and L1 is not the origin, then the robot does not form a cycle, because we've checked all of the, because those are the 4 scenarios we checked first. No, I'm talking backwards. If D1 is n and L1 is not the origin, then the robot does not form a cycle, because that's what we just proved here. If it's not the case that D1 is n and L1 is not the origin, then the possible scenarios are these 4 that we have laid out. And we have shown that in all 4 of these scenarios, the robot does form a cycle. And therefore, this if and only if statement holds. Okay, and that's our proof that this algorithm that we've defined works. So basically, all we need to do is we need to check if the robot we need to check, all we care about is what happens after the first run through the instructions. And we need to check, does the robot after running through the instructions, is the robot facing, let's see here. So yeah, is the robot, is the robot facing north and not at the origin? Whether or not this is true or false will give us the response that we want. Okay, so let's code this up. Okay, so the way we're going to do this is, instead of dealing with north, south, east, and west, we're going to have the directions stored in a list. So we're going to have north, which is 0, 1, because this is so this is like 0 in the x direction and positive 1 in the y direction. That's sort of a vector pointing upwards, and so we will associate that with north. We have 1, 0, so this is pointing 1 unit to a vector pointing 1 unit to the right. So this is going to be east. South is going to be 0, -1, and then west is going to be -1, 0. Okay, so I'll just write the meaning north, east, south, west, just that we know. So going to have x and y. So we're going to keep track of the position of the robot. And we will keep track of the position using the x and y coordinates, which we will set to 0. And we're also going to have a direction index that instead of referring to the direction itself as using n, e, s, or w, we're going to have a index which refers to one of the entries in this list of directions. And that's going to correspond to the direction that we want. So we start facing north, or the robot starts facing north, and that's the first entry in this list, and so that is index 0. I'm not sure how I feel about using like a bunch of like assignments with commas, but whatever, it's fine. For I in instructions, this might not be great notation because we're used to using I for like integers, or like yeah, to refer to natural numbers when going through like a loop. So this might be a little bit confusing. Actually, yeah. Let's just do instruction. It's fine. We're typing. It doesn't take too much extra typing to type that. So for each instruction, if this instruction is G, then we're going to go forward one direction. And how do we define going forward? So we're going to move the X and Y coordinates, and we need to move them either 1 unit north, east, south, or west. And the direction we move them depends on what direction we're facing. And we know what direction we're facing by the direction index. So what we can do is we could just take directions, look up the direction index, and take the first coordinate. Because like here for facing north, the direction index is 0 because this vector corresponds to north. And then to move north one direction, you don't move at all in the x direction, and you move +1 in the y direction. And so we get the first entry here using that index, and then for y, same thing, but we get the second entry because that's the y, that's how many units we move in the y direction. Okay. So if the instruction is not go, it's either going to be left or right. So if it's left, then we need to move left one. And this is one of the nice things about how we've written out this directions. So we did these in order north, east, south, west on purpose, because if we're turning left, then all that means is that we're going back one entry in this direction list. So if you're facing west and you turn left, then you're facing south. If you're facing south, you turn left, you're east, east, left, north, north, you turn left, you're facing west. So you go back one. So we have to update the direction index. And so we just take the direction index and we subtract 1. But if we're here facing north and we turn left, we want to end up back at W. So we want to wrap around. And so this is modular arithmetic. So we want to take the division, we want to find the remainder after dividing by 4. So if the direction index is, so if we start with the direction index at 3, 2, or 1, then this is not going to do anything because the remainder after dividing by 4 is just going to be the value because 4 does not go evenly into any of those numbers. Yeah, neither of, and all of those numbers are strictly less than 4 and positive. So there you go. But if we're at 0 and we subtract 1, then we're going to end up at -1. And the remainder after division with 4, that's going to end you back up at 3. Okay. So yeah, this is basically allows us to do modular arithmetic. And that works. Otherwise, I could write else. Because let's just check here. Instructions is always going to be a valid instruction. So I could just write else, but just to make the code really easy to read, otherwise, if the instruction is R, or I wonder if we could even do like this. Otherwise, instruction equals R. But this doesn't look quite as nice. You know, that probably would have been better because it would run faster because you're checking less thing, but this is fine. It'll work. So here, the same thing, but we add 1, because when turning right, you just go forward 1 in this list of directions. We use modular arithmetic here. Then we return, okay, so remember, we want to return true if there exists a circle such that the robot never leaves the circle. Okay, so we know that the robot leaves the that the robot goes off to infinity. Under what conditions? It needs to be at the origin. No, it needs to be facing north and not at the origin. And the negation of that is the direction index needs to be not equal to 0. So the negation of that is either the direction is not north or the direction is north and we're at the origin. So either the direction is not north, meaning that the direction index is not 0, or the direction index is 0 and we're at the origin. But we can just simplify that and check if we're at the origin, because if we're at the origin, it doesn't matter what direction we're facing. X equals 0 and y equals 0. Okay, so here is our code. Let's submit it. And there we go. So, I guess the only thing I didn't really describe here was, or I didn't describe the process before doing it, but the thing that really helped us out here to make our code nicer was to create a list of directions so that we could refer to the directions without using north, east, south, and west as strings. And furthermore, we had to be clever in choosing how to list these directions, because listing them in this order allows us to change direction in this way by sort of like going back and forth through this list. So that's one thing that I didn't talk through, but otherwise we gave an extensive proof of why this code works. And so yeah, that's how we come up with this solution, and that's how we prove that it works, and this is how we do it. So there we go.